In the last few lectures, we've been going through all the stuff that you need to know in order to understand the statistical thermodynamics of ideal gases. And now we're ready to apply that in the general case. Earlier we applied it just to monatomic ideal gases. Now we'll be able to apply it to every kind of ideal gas. And the emphasis here will be on understanding what's going on, what contributes and what doesn't contribute to the properties, the thermodynamic properties of ideal gases. And it turns out that once you understand ideal gases, you understand a lot about every system as well. This material is mostly from chapter 15 of Engel and Reed. I've added a bunch of stuff that isn't in Engel and Reed, and a lot of comments and stuff especially that aren't in Engel and Reed, but the gist of it and the backbone of it is all chapter 15 in Engel and Reed. Okay, so in previous lectures we saw that the overall partition function, just to review a bit, for the whole ideal gas, all capital N molecules, all Avogadro's numbers of ideal gas molecules, is Q to the N over N factorial, where Q is the molecular partition function. And each molecular partition function itself partitions or factors into a translational, a rotational, a vibrational, and an electronic partition function. And then we went down that list and found expressions for all of those things. So for the translational partition function, we saw that it's just the volume that the gas occupies divided by this de Broglie wavelength, the thermal de Broglie wavelength cubed, so it's really a thermal de Broglie volume. We saw that that partition function contributes a lot of microstates. There's a lot of translational microstates because the box that the molecules are in is big, is macroscopic. We saw that the rotational partition function is very simple. It's just the temperature divided by a vibrational temperature that depends on the moment of inertia for the molecules, and a symmetry factor that depends on the symmetry of the molecules. And as we've seen in calculations, and we'll see more in calculations down below, that has a typical kind of medium value I've called it here, around 100, maybe 1,000, oftentimes smaller than that, oftentimes just a few, but somewhere between maybe about 10 and a few thousand. That's the range of rotational partition function values. And so I call it medium, but it's way smaller than the translational partition function. Then there's the vibrational partition function, which accounts for the fact the molecules can vibrate. And we saw that that isn't quite so. Oh, before I leave the rotations here, let me again point out that there's two cases, right? There's the linear molecules case, which applies to diatomics, but also linear polyatomics like CO2. And then there's the nonlinear molecules case that applies to everything else, and it's a little bit more complicated, but not much. Remember also, while we're here, that that the vibrational temperature is the thing that reflects the molecular properties in this case, and there's really only that one molecular property. The other features of the molecule don't matter. It's really just the moment of inertia which controls the vibrational temperature. And for polyatomic molecules, there are 3 vibrational temperatures because there are 3 principal moments of inertia. All right, returning to the vibrations then, we saw that there's this factor that accounts for the number of microstates that are occupied, the number of vibrational microstates that are occupied. And then there's this 0-point energy factor that's in there or not, depending on what you're doing. You can leave it out or put it in depending on what you're doing. We're going to keep it in this case, and shift it around, as we'll see. We'll do a fair amount with that ZPE factor, because it turns out it's important for chemical reactions in the end. I've said earlier that these ZPE factors, there's one on the electronic vibration function down here, these ZPE factors can be set to 0 if you've only got a single molecule at a time. But if you're dealing with a chemical reaction, then by definition you always have more than one chemical reaction at a time, And that means the ZPE factors become important. You have to keep track of them. And so we won't quite ignore them most of the time here. We'll keep them in. They're kind of a distraction and an annoyance because they don't do much most of the time. But when we get to chemical reactions, they become important. So we'll keep them in. All right, finally that leads to the electronic partition function. And usually even the first excited state, electronic excited state, is too high in energy to have any appreciable population. And so most of the time, with a few exceptions, the electronic partition function just reduces to the ground state degeneracy, and this is called G sub E, or just G by Engel and Reed. It's the same quantity. I use W because it's the same W that appears when we were talking about entropy way back in the beginning of the class, and I want to emphasize that. For some reason, the names change in some of the StatMech literature, but it is the same old W we have seen from the beginning. Anyway, it's just the ground state degeneracy times another ZPE factor, which we will leave out or keep in depending on the needs of the moment. All right, so that's all from before, but now we're going to try to apply all this to the thermodynamic properties of complicated ideal gases, polyatomic ideal gases eventually. And so let's do that using, as before, as with the monatomic ideal gases, using the Helmholtz free energy, an expression, a statistical expression for the Helmholtz free energy, as our starting point. And really, that gives us everything, right? The Helmholtz free energy is a fundamental thermodynamic potential. You can get everything else from it. That's the program we're going to follow in this case. We're going to use that A to get everything else. Here it is in general with just a generic partition function, molecular partition function Q plugged in, and there's not too much to say about it, except that that's the mathematical expression we can use. Here it is again where I've plugged in this expression for Q that includes all the little substate partition functions, but there isn't too much of use in either of those expressions. They're just our starting point. So the very first thing we want to do is calculate the pressure equation of state, and we do that just like we did before with monatomic ideal gases. We do it by taking the derivative of the Helmholtz free energy with respect to volume, holding temperature and mole numbers constant. That's a true relationship that comes from thermodynamics. And I won't go through the algebra. In fact, in general, there's a lot of these. StatMech has just an enormous number of relationships, hard to keep track of even, and a lot of derivations, right? Lots of algebra. I'm not going to go through that algebra. It's in the notes. Much of it is in the notes anyway. And if you want to go through it, and I recommend that people do go through it, you can do that. But I don't want to spend sort of class time here or video time going through every little algebraic manipulation. Anyway, if you take that derivative and do some algebra, then you get the ideal gas law. These are ideal gases. They better obey the ideal gas law, and if the statistics are right, we'd better get the ideal gas law out of our statistics, and in fact we do. There it is, PV equals nRT. That's true for all gases. I've mentioned in the past that the ideal gas law is universal for all ideal gases. It doesn't depend in any way on the properties or structure or even chemical identity of the gases involved. And that's what we're seeing here. It's really just a reflection of the translational partition function. This term here comes from the translational partition function, and that's the only term that contributes. And so this V that we're seeing over here in the translational partition function, that V right there, is the origin, of the ideal gas law that we're seeing over here. And that's the only thing that contributes. It's a pure translational effect. All right, next thing is the internal energy, E, which is the same thing as the thermodynamic. Your book calls it the internal energy, the thermodynamic energy. It's also the mean energy for our system in question, the system being our collection of N ideal gas molecules. Here's the way we calculate it. There's some algebra, but the main point of this algebra is this relationship down here. It says that the thermodynamic energy, internal energy for an ideal gas, is a sum of contributions. There's a translational part. There's an additive rotational part. There's a vibrational part, and there's an electronic part. And if you can calculate each of these separately, you can just add them all together to get the total thermodynamic energy. That's a really useful property. It means we can look at the contributions from each subsystem within the molecule one at a time and see how much they contribute and why they contribute what they do. So, first of all, the translational part. We already did that. That was part of the monatomic ideal gas, right? Every molecule has a center of mass, and the translational part is just talking or just dealing with the consequences of the movements of the center of mass. Doesn't matter whether it's an atom or a protein, they all have a center of mass, and they'll all have this 3/2 nRT contribution to the total energy. Next comes the rotations, and that's new. That's not something that we did earlier in the monatomic case. There are no rotations for atoms. And since there are two cases for the rotations, the linear case and the nonlinear case, there are also two possible contributions to the rotational energy, the rotational internal energy, and working out the algebra, that turns out to be just nRT for the linear case. And linear means either diatomics, right? All the diatomics have to be linear, or polyatomics like CO2 that are also linear. This case applies to all those cases, or let's say HCN. All those cases, all linear triatomics or linear, well, things like even acetylene, for example, which is also linear, all those molecules, this case applies. And if it's a nonlinear molecule, then it's 3/2 nRT, and the reason is basically that the nonlinear molecules have an extra rotation that has to be accounted for. So this is really 2 times 1/2 nRT, and this is 3 times 1/2 nRT down here. 2 because there are only 2 rotations necessary for linear molecules, 3 because there are 3 rotations necessary for nonlinear molecules. Notice, though, that the rotational energy doesn't depend on anything other than the shape of the molecules. It's just like this case up here for the translations. Doesn't depend on the mass of the molecules, doesn't depend on the moment of inertia of the molecules, doesn't depend on the bond lengths of the molecules, doesn't depend on anything except their shape. If it's linear, you get one case. If it's nonlinear, you get the other case, and that's the only thing it depends on. So the energy contribution due to rotations is another almost universal contribution to all ideal gases. That brings us to the vibrations. And once again, we're going to use the standard formulas for doing these calculations. And there is now a slight contribution, or a slight complication, in the case of vibrations, and that is that polyatomic molecules have normal modes. A polyatomic molecule with n atoms will have either 3n-6 or 3n-5 vibrations. 3n-5 for linear molecules, 3n-6 for nonlinear molecules. And so if I have anything more than 2 atoms, there's more than one normal mode. It turns out, though, that the whole vibrational contribution from all the modes combined is just an additive sum again of the contributions from each normal mode. So again, we can go right down the list. We can calculate the contribution from mode number 1, from mode number 2, from mode number 3, and so on, and just add them all up. That total is the total contribution from all vibrations. I'm going to use a notation from now on out that I hope doesn't confuse people, but I'm going to pretend that every molecule has more than one normal mode. In other words, I'm going to put these sums in, and I'm going to put products in and stuff like that, as if there was always more than one normal mode. Of course, obviously, diatomics only have one normal mode, and in that case, the sum only has one term, or the product only has one term, but I'm going to keep the products and sums as if there were more than one normal mode. So it covers all cases, not just the diatomic cases. And I'm not going to separate those two possibilities, so watch for that. All right, then we can start looking at each normal mode. We do a little bit of algebra. We substitute in the vibrational partition function. Notice that I've kept the ZPE factor here. So I'm going to get the answer with the 0-point energy kept intact for the moment because, again, at the end we'll need it. And if you do that, then you get a vibrational energy that has the ZPE term. So again, this is just the 0-point energy term. And notice it's just 1/2 h nu. That's the 0-point energy multiplied by however many molecules there are. So this really is just the total ZPE energy. And it's just an additive contribution. And then the contribution that comes from the actual population of the various levels in the ladder of vibrational states. This term will be small if the temperature is low enough so that you're only populating the ground state mostly. If you start to get a little bit of population into the second state, it'll still be small. This extra term, the non-ZPE term, only starts to get significant when you start getting significant population into several vibrational states for a given normal mode. We'll see this over and over again. What that means is that under most circumstances, the vibrational contribution to the energy isn't very large. There are exceptions to that. We'll see that when we look at examples down below. But for the most part, it's not very big. A lot of the time, we can just ignore it. All right. I've just rewritten things here so that everything is in terms of the vibrational temperatures for each mode. So theta V sub I here means the vibrational temperature for the ith normal mode. Oops, sorry, over K. So these theta V sub i's have the vibrational frequency for mode I buried inside of them. And this is just this formula below is just the same as the formula above, except that I've put vibrational temperatures in everywhere instead of leaving things in terms of the vibrational frequencies themselves. Let's see, is there anything else I need to say about that? Over here on the right, I've written the vibrational partition function here as the part that counts, that really counts, that matters, times this 0-point energy factor. And I want to point out that that same kind of thing is going on over here. So the 0-point energy factor is the thing that gives rise to this first term, which is just the 0-point energy term. And everything else, the thing that actually counts microstates and takes into account the effects of microstates, a population of microstates, is the rest of it, which is typically small. This ZPE factor will sometimes be set to 0 when we set the 0 of energy appropriately. So this is the part that really matters, and it's oftentimes small. All right, finally the electronic contribution. Most of the time this is just the 0-point energy factor. So here's that result down here. Here's the 0-point energy, and here I've written the 0-point energy as the number of moles of gas molecules times the molar 0-point energy. This is the number of gas molecules, period, times the energy of any one molecule. So these are just different units. But when there's no population of even the second excited state, it's just like the vibrations. When the electronic energy levels are only the ground state is populated, then there's really only the ZPE term that contributes to the energy, and sometimes we'll be able to set that ZPE term to 0. So very often, the part that counts microstates is 0 for the electronic contribution. Okay, putting everything together then, here's the whole business all at once. Here's the translational contribution, here's the rotational contribution, here's the vibrational contribution, and here's the electronic contribution. And you'll see that there's no contribution here from W0, from the ground state population. And that means that if we don't get any contribution or any appreciable contribution from the second excited state, then this whole term will be 0. And that's true most of the time. And then there's one more contribution tacked on here, and that's the total 0-point energy of both vibrations and electronic states. I've gathered them all together into one term. So here's what that is. The 0-point energy with a bar on top means per mole is Avogadro's number times the 0-point energy for a single molecule. And that EZPE, that ZPE here means the total 0-point energy from both vibrations and electronic states. So here's what it is. It's 1/2 h nu for all the normal modes in the molecule. Again, if it's an atom, there are no normal modes. If it's a diatomic, there's only one normal mode. If it's a polyatomic, then there are many normal modes in general, plus the 0-point energy for the ground state electronic manifold. So, so that's always there, and a lot of times it can be set to 0. If you've only got one kind of molecule in your system, you can set this to 0 and just ignore the 0-point energy. But again, when we're doing chemistry, by definition, in those cases, you have more than one molecule around, and then you've got to keep track of those 0-point energies. There's an overall 0-point energy that you can always set to 0, but that's got to be the overall energy for all molecules at once. You can't do it one by one for each molecule. And so as long as you've only got one kind of molecule, you can set this to 0. As soon as you start having many molecules, you've got to keep track of them so that you don't lose track of the energy differences between the various molecules involved. Okay, now that's the total overall energy contributions. These first two terms are the dominant ones usually. Those are the translational and rotational contributions. Usually these other two terms, this one's oftentimes really 0, and this one's oftentimes small. So let's make the approximation that we can neglect these last two terms and see what we get. In that case, the total energy for any ideal gas molecule becomes really simple. It only depends on the shape of the molecule. It doesn't depend on any other molecular properties. It's very nearly universal for all molecules. It's 3/2 nRT for a monatomic, because it doesn't have any rotations. It's 5/2 nRT for a linear molecule, and it's 3 nRT for a nonlinear molecule. And that's it. Any molecule, no matter what its structure or what atoms are inside of it, the internal energy, the thermodynamic internal energy, is one of these three cases as long as vibrations can be neglected, as long as vibrations aren't contributing. Later down, we'll look at a whole slew of molecules and see how good that approximation or that assumption is, and we'll see that it's pretty good most of the time, which means that this case is a pretty good initial guess. If you don't know anything about your molecule and you want to know something about its internal energy, if you just guess that vibrations don't contribute, most of the time you're going to be not too far off. All right, and that's just what I'm saying down here, so you can look at that later. All right, so that's the internal energy, but once we have the internal energy here, all we got to do is take a temperature derivative, and we can get the heat capacity. And since the internal energies add up, and all we're doing is taking derivatives of all those terms, the heat capacities also add up. So the nice thing about both internal energy and heat capacity is there's just an additive contribution from every subsystem. There's a contribution from translations, a contribution from rotations, one from vibrations, and one from the electronic states. And you can expect from the fact that these two guys are usually small, vibrations and electronic are usually small, that the contributions to heat capacity are also usually going to be small. And so the main dominant contributions to heat capacity for most ideal gas molecules are just from the translations and rotations, and those are pretty much the same. They only depend on linear, monatomic, or nonlinear. There's really only three cases for those cases. And again, that's the good first approximation. Let's see how that works out. First of all, for translations, the heat capacity, we've already seen this, right? For monatomic ideal gases, the heat capacity is 3/2 nR. We've seen that before. The molar heat capacity is just 3/2 R. We used that many times earlier in the class. Now you can see that it's an automatic consequence of the translational contributions to every molecule. It's always there. Every molecule has this. Some molecules don't have the other things. Atoms don't have the other things, but every atom, every molecule has this translational contribution of 3/2 R. You can't have a heat capacity that's any smaller than 3/2 R. And for the record, 3/2 R is equal to 29.2 joules per K per mole. Or sorry, not 29.2, 20.8. That 29.2 is for a different case. 20.2 joules per K per mole. That's the smallest value that any ideal gas heat capacity can have. Heat capacity at constant volume, CV, can have. Then there's a rotational contribution. That means just taking the derivative of the results we had before. That gives nR for linear and 3/2 nR for nonlinear. Again, this is 2 times 1/2 nR for 2 rotations of linear molecules, and 3 times 1/2 nR for the 3 rotations that nonlinear molecules have. So again, the 2 main contributions are universal. They don't depend on any molecular properties except for whether they're monatomic, linear, or nonlinear. Now the vibrational contribution. Bunch of algebra in here. If you take this derivative of the vibrational expression we had up above, then you get this expression or this expression in terms of vibrational temperatures. And I'll come back and look at that a little bit. But it's usually small. You can tell when the contributions, the vibrational contributions to either energy or heat capacity will be small by comparing the temperature you're at to the vibrational temperatures. So if you compare T to theta vibrational for each mode in the molecule, and if T is much smaller than that vibrational temperatures tend to be around thousands of degrees. Let's say about 2,000 degrees is a typical one. And so if you're at a temperature like 300 K that's much smaller than the vibrational temperature, and if that's true for every single mode in the molecule, then this vibrational contribution to both heat capacity and the internal energy will be small. If, on the other hand, T starts to approach the vibrational temperature, or if the vibrational temperature is small, for example, itself, so for example, for I2, the vibrational temperature is 308 K, so it's almost the same as room temperature, then in that case you will get considerable contributions. So by looking at the vibrational temperatures, you can tell whether or not both the internal energy and the heat capacity will have serious contributions from vibrations or not. So usually the vibrational temperatures are much higher than room temperatures, so at room temperature at least, the contributions to the heat capacity, the vibrational contributions to the heat capacity are small. Notice also that the heat capacity, the total vibrational heat capacity, is just a sum of contributions from each of the normal modes. And so once again, you're going to get a vibrational contribution from each normal mode, and the total vibrational contribution is just adding them all up. All right, then finally we get to the, there's a few comments here, but we'll make those comments later down anyway. We get to the electronic heat capacity. If the first excited state is not populated, as is usually the case at room temperature, then the electronic heat capacity will be 0. There's just no place to put the energy, right? The heat capacity is about raising the temperature a little bit and then storing some energy in your molecule as a result of raising that temperature. And if you're not populating that first excited state, there's no place to put extra energy. And so until you start populating the first excited state, the electronic heat capacity is 0. It is very rare that, at room temperature anyway, that the electronic degrees of freedom contribute anything to the heat capacity. There are a few exceptions to that. There are a few molecules with very low-lying first excited states, and then you do get a small contribution from the electronic heat capacity. But the electronic heat capacity is generally small in pretty much every case, unless you start getting up to high temperatures like thousands of degrees, starting to rival the temperature at the surface of the sun, for example. All right, so here it is all put together. The total heat capacity for a diatomic molecule is a translational contribution, a rotational contribution, and a vibrational contribution. And there's also, in principle out here, an electronic contribution, but I've set that to 0. It happens so rarely that that contributes that I've just ignored it here. Again, if we ignore the vibrational contributions, just like we did for the energy case, and sort of use the first two contributions, the translational and rotational contributions, as our baseline, our simple baseline for understanding what's going on, then everything gets simple again. We don't have this big complicated vibrational piece anymore. And so, once again, the heat capacity only depends on the shape of the molecule. It's 3/2 nR for monatomic ideal gases, so for noble gases, basically argon, helium, xenon, and so on. It's 5/2 nR for linear molecules, and it's 3 nR for nonlinear molecules. And of course, for an ideal gas, the Cp, the heat capacity at constant pressure, is just Cv plus nR, and so we've now also got the heat capacity at constant pressure, Cp, and that's just 5/2 nR for a monatomic ideal gas, 7/2 nR for a linear molecule, and 4 nR for a nonlinear molecule. So very simple again. What's good about the Cp value is that this is in tables. In fact, it's in tables in Appendix A. And so we can compare values that we compute for Cp directly to values that have been measured and entered into the tables in Appendix A. And notice that this relationship, that Cp is equal to Cv plus nR, that's always true for all ideal gases. And that means that even if vibrations start contributing and our simple cases here start to break down, we can still get, that doesn't affect the fact that heat capacity, that Cp is just Cv plus nR. And so these relationships and all these relationships, right? I mean, this Cv here also gives us Cp. So if we just add nR to the end of this relationship, we can get Cv. Which means we can do a lot of comparing to experiment or to tabulated values. And here's that comparison. So let's look at what we've got here. We've got a whole bunch of molecules now. And for every single one of them, we've got a Cp value, a Cp per mole, right? The bar here means this is a molar heat capacity, which just means that n is equal to 1 in all these formulas up above. We just put an n equals 1 in all these formulas above, and we've got molar heat capacity. So, first of all, for the monatomic cases, argon and xenon are the only entries in the table in the back of the book. Of course, we can get the ones for the other noble gases too, but they're identical. To 3 decimal places at least, they have no difference whatsoever. There's no vibrations or rotations in this case, and so the only way that argon and xenon and other noble gases could differ from each other is if they had electronic contributions that were contributing. And that undoubtedly does start happening when you get to high enough temperature. If you're at thousands of degrees, probably the heat capacity of argon and xenon and other noble gases start to differ from each other because they have different electronic structures. But at least at room temperature, the fact that these guys are identical, what that means, of course, is that the electronic contributions aren't doing anything. So just like I said earlier, usually the electronic contributions don't do anything. Here's the 5/2 nR value. It's 20.8 You know what? I said the wrong thing up above. I said that that was 3/2 NR. Please correct that in your own mind and in your own notes. The 20.8 value is actually 5/2 NR. That's the smallest possible CP value, not the smallest possible CV value. Sorry about that. I'll see if I can correct that. All right, now all the diatomic and linear molecules, especially all these diatomics. Let's look at those. First of all, let's calculate the value you would get if there's just translations and rotations ignoring vibrations. It's 29.1. Look at all these values. They're not quite all 29.1, but they're all close. The only exceptions really that are a little bit bigger is the one for F2 here. We'll talk about that case. Down here for NO, it starts to get a little bit bigger. And then down here for Cl2 and Br2 and I2, they start to get significantly bigger. And we'll talk about all those kinds of exceptions. But the basic rule is that all these values are very close to our universal rule of just translations and rotations, 29.1 joules per K per mole. First of all, let's look at H2 here. It's a little bit too small. This is supposed to be the minimum value of heat capacity that you could possibly get for a linear diatomic molecule where vibrations aren't contributing, and it's a little bit below that. How'd that happen? Well, what's happening in this case, remember when we did the rotational contributions, we made a high temperature approximation. We assumed that the rotational states are close enough in energy that a discrete sum could be replaced by a continuous integral. That's the classical approximation. In other words, we're treating the rotations as if the molecule were a classical molecule, ignoring the effect of quantum mechanics. But that was an approximation for hydrogen, which is very light, which has relatively widely spaced rotational levels in its quantum model. That's not quite accurate. And so you can see the difference isn't very big. It's only a few tenths of a joule per K per mole. But it's visible. So this is one place where the quantum effects actually have a visible effect on the value that you see in real life. Everything else, though, for molecules, even for D2 here, which is only slightly heavier than hydrogen, all the way down, they're all either this big, 29.1, or a little bit bigger. N2, it's 29.1 exactly. HCl, HBr, all 29.1 exactly. O2, just a little bit bigger. F2, a fair amount bigger. Let's see, NO, a little bit bigger. What's happening in those cases? I'm not sure. I haven't actually done the calculations, but I'll bet if you calculated the vibrational contributions to those three cases, you'd find a little bit of contribution from the vibrations. So probably these are vibrational contributions coming in. Not very big, you can see, but enough to see. All right, now we get down to these heavy diatomics. Cl2, Br2, and I2. What's going on there? Now we were starting to get significant differences between our 29.1 value, our universal 29.1 value up here, and what we actually see experimentally. And now I actually have done the calculations for at least I2 in this case. And what's happening is that I2 has quite a weak bond. Its vibrational temperature for that soft bond is only about 300 K. Normally they're in the thousands of K, remember. Now it's only about 300 K. That's room temperature, which means that looking at the vibrational temperature for I2, we'd expect serious contributions from vibrations to the heat capacity and also to the internal energy for I2, and that's what we're seeing. And it's differing significantly now by about 7. Yeah, about a little bigger than 7, actually, joule per K per mole from our universal value up here. And to a lesser extent, that's also what's happening for Br2 and Cl2. I haven't actually done the calculations in those cases. You can do the calculations yourself. You can calculate what the vibrational contribution will be to chlorine and bromine from vibrations and see if those contributions are big enough to account for the differences that we're seeing experimentally, and I'll bet they are, and it would be an interesting and useful and helpful exercise, good practice to do that. All right, so vibrational contributions to these three. Now let's look at the linear but non-diatomic cases. So these are cases where they're linear but three atoms in these two cases, and like acetylene, for example, has 4 atoms. So some small number of atoms but still linear and not just 2 atoms. And now you can see that the heat capacities are consistently larger than you'd expect just on the basis of of rotations and translations. And so it must be that vibrations are entering in here. And again, you can do the calculations, you can do the vibrational calculations in this case. Notice that there's more than one normal mode for each of these molecules. So a diatomic only has one normal mode, but a triatomic has, a linear triatomic has 4 normal modes, and so each normal mode contributes. So if there's even one soft normal mode, then it will contribute considerably to the heat capacity. And the soft mode for these two molecules is the bending mode. So let's just write down the normal modes for CO2, for example. So for CO2, the normal modes, remember, are a symmetric stretch, an asymmetric stretch, and 2 bending modes, one that's in the plane and one that's out of the plane. These guys both have high vibrational frequencies and high rotational temperatures, so they don't contribute. If you look at the contributions from these, they're totally negligible. But these two guys both do have fairly low frequencies and low vibrational temperatures. The vibrational temperatures, if I remember right, are about 700 K for these two cases. In other words, they're not quite room temperature. They're still twice room temperature, in fact. But they're starting to get close enough to room temperature so that you get significant contributions. And there's 2 modes, and each of the 2 modes adds, and so you're getting a double contribution from both of these 2 soft modes. So if you're wondering, in some molecule, some polyatomic molecule, whether or not vibrations are contributing to the heat capacity, look for soft modes and look for how many soft modes there are. Even a few soft modes can make contributions that are significant, and that's what's happening in these 2 cases. All right, finally, we get to the nonlinear molecules now. Now our baseline universal value for just translations and rotations is 4 times R, which is 33.3. That's the value we expect if there are no vibrational contributions. And you can see that we're generally close to 33.3, especially for water here, but always a little bit above 33.3. And that means that there's vibrational contributions coming in and playing some role, not a very big role, you can see. They're still all close to 33.3, but playing some role at least in all of these molecules. Why is that? Well, you're starting to have a large number of atoms, right? 4 atoms for ammonia, and it's nonlinear. So the number of normal modes for ammonia is going to be 3 times 4 minus 6, which is 6 normal modes for ammonia, and every one of them contributes, right? There's now 6 vibrational contributions to this molecule. And so even though each one of them is rather small, they add up. If you start getting a lot of normal modes, you start getting a contribution from vibrations, even if each normal mode is pretty stiff, even if you don't have any soft modes. I don't think ammonia has any soft modes, but there's a lot of them. There's 6 of them now. So they add up, and that gives a value of 2 more or less added to the heat capacity for ammonia. Methane here has 5 times 3 minus 6, that's 9 normal modes. And yeah, you can see, and they're all rather stiff modes. None of them are soft. And yet still, with 9 normal modes, that's enough to make a serious contribution to the heat capacity. Finally, let's look at some cases where we really don't, our theory should break down for these cases. So here's ethane, right? It has an internal rotation. It's not a rigid molecule at all. So our rigid rotor approximation isn't even good for this molecule. And accordingly, we're getting a much larger heat capacity than you'd expect from our universal rigid rotor approximation here. 52, which is much bigger than any of the heat capacities we've seen above. That's due to 2 different things. First of all, there's this internal rotation, yes, which means there's an extra rotation in this molecule. It's now breaking our earlier rules. And it also has a lot of normal modes. There are 8 atoms in ethane, 17 normal modes, and each one contributes. I don't think any of those normal modes is soft either, but there's just enough of them to contribute significantly, and so you get a heat capacity of 52. Here's benzene. Benzene is a rigid molecule, so a rigid rotor approximation is okay in this case. We don't have any internal rotations or any other funny business like that going on. But now there are 12 atoms. 3n minus 6 is 30. There are 30 normal modes, and some of them are soft. So down here, and you can expect, right, the bigger the molecule is, the more likely it is there's some way to bend that molecule or deform that molecule that doesn't cost much energy, right? You're getting a great big thing. It starts to get floppy. Even benzene, which is about as rigid a large molecule as you can get, has some soft modes. Here are the soft modes over here on the right. I looked these values up. Here are here's the vibrational temperatures for some, there's 30 vibrational temperatures for benzene because it's got 30 modes. 2 of those vibrational temperatures are quite low, 534. And so there are some soft modes in benzene, and those are undoubtedly contributing significantly to this heat capacity of 82.4. But there's also 28 other modes, and the collection of all of them is just probably the main reason for this rather large heat capacity for benzene. In general, as the molecule gets larger and larger, you get more and more contributions from rotations, from internal rotations, and more contributions from normal modes, from lots of normal modes, and so the heat capacities go up. And I think all this is just making the comments that I just made. The next topic we're going to talk about is chemical potential, which is, of course, the big one for chemists and will lead to our statistical understanding of what drives chemical reactions. So we'll stop here and take that topic up next time.